First of all, let me thank the organizer for inviting me to this very nice conference. And I will present some recent results which are connected to the talk that we had in the morning. Let me also thank the collaborators. I have this project from the theory side, a long-standing collaboration with Claudio Castellani. It's Sapienza Goethe Cyborg, who is really the main driving force behind the numerics I will show today. And then three guys who are in Rome working with me, Matteo Udina, Jacopo Torre, and Niccolo Stellati. And then this recent experimental collaboration with Peter and Kota about this, say, the Higgs mode in superconductor. So what I will give you today is a theoretical perspective.
Lara, can you speak in the mic?
My perspective? Yes, sorry. Don't we have another microphone or something? Okay. So I will give you my perspective on why it's interesting trying to understanding conventional spectroscopies on superconductor, and why this should be interesting also for those who are not working on superconductor actually. And so let me first define what is unconventional for me, and then I should start from what is conventional spectroscopy, which is somehow detecting properties of material using weak light pulses which are very high resolved in frequency. And this is something that we know. For example, if you want to measure reflectivity of a sample, what we get is the electric function, which is connected to optical conductivity. Now, for a theories, we know what is optical conductivity. So we know that we have to compute the current correlation function, and there is no discussion about this. Eventually, we don't know how to compute the current correlation function in a correlated system, but there is no ambiguity on what experiment is measuring and what we should do in theory. Now, when we go to experiments done with very strong light pulses and which are eventually time resolved in the access, in the experiment, things are different. So very broadly speaking, we have an experiment where there is some strong pulse, and then there is a probe coming after some time delay. And then what we detect is some change of this probe. This can be done in reflection, in transmission, in several combinations. But then the theoretical challenges we have are at least three. In principle, we should describe metastable state in their relaxation. And this is a very hard theoretical problem that I will not even try to discuss today. Then for sure, we will need to compute the nonlinear response, which means that we have to compute the current, which is third order somehow in the electric field. This because strong pump generates this current in the material. And then we have to establish a link between what is measured in the experiment and what we can compute in theory. And even this link is not so obvious very often. And this also makes ambiguity in the way we have to interpret the experimental result. So I will give you my perspective today, how trying to address these two problems within a kind of equilibrium, quasi-equilibrium approach, in the sense that we just want to go next order in a perturbation theory, in the power of the current as a function of the field, in the context of superconductor, gave us some insight about what we should do. So this also means that I'm talking about terahertz spectroscopy with fields which are not strong enough to melt the superconductor, okay? And let me just make a parenthesis of what is the problem of nonlinearity. In principle, we know example where there is no problem of computing nonlinearity. And let me take the example of phonons in insulator. So the phonon is just a vibration of the system, which spectral function is dominated by the frequency of the phonon. And then if the phonon is Raman active, it is quadratically coupled to light. And this means that if we integrate out the phonon from the probe, we get a contribution to the effective action of the electric field, which is fourth order in the electric field. So the current, which is just the derivative of this guy, is third order in the electric field. What I'm saying here is just, if I want to know how a phonon mode can contribute to the nonlinear response, what I need to know is what is the spectral content of the mode, so what is the frequency of the phonon, and how much it is coupled to light.
So and then this is a Raman scattering of the old.
This is a very, trivial, pump probe experiment in phonons and insulator can be, for example, the case. This is just a general approach. So phonons that.
No, but this is this a Raman scattering in an insulator?
Raman scattering.
Right.
Raman scattering, but
okay.
even
spontaneous Raman or stimulated or.
Spontaneous Raman can also be some kind of stimulated Raman.
Okay.
Okay, so there are differences, but this is the general idea. So, I mean, these are quantities that people can compute in DFT in ordinary materials. So this is not a problem. And why somehow the problem is simple? Because we have a kind of adiabatic decoupling between the electronic and bosonic degrees of freedom, in the sense that when energy of the phonon is much smaller than the electronic gap, I can somehow integrate out my fermions, which just give rise to the Raman visibility of the phonon, and then the problem is simple. But when we go now to metals, in particular to superconductor, we cannot somehow decouple these degrees of freedom. And this is a very sketchy way to represent the spectrum of a superconductor. So in the superconducting state, we have an order parameter which is complex. The equilibrium value of the order parameter is what appears in the spectrum of the electronic excitation. So fermions are gapped in the superconductor. Then we can have collective modes, which are amplitude and phase. And then these are essentially bosonic in character. These are collective electronic excitation. The spectrum of the Higgs essentially overlap with the quasi-particle continuum, because this is just a projection of the quasi-particle continuum in a specific symmetry. And the plasmon is usually very high energy, so not relevant for terahertz. Unless we have, for example, a system like layered cuprates, and this was mentioned by Andrea this morning, where there is a very soft plasma energy connected to phase fluctuation between the planes. Okay, so this is the system. And then you see that here we don't really have a decoupling between what is fermionic and what is bosonic in nature. And this makes somehow the description more complicated. Or if you want, we have to start from microscopic model, and then we have to deal with single particle excitation and collective modes at the same footing. So the way people have been thinking about this problem over the years has been, again, a kind of simplified but eventually reasonable approach. First of all, let me say that we completely forget about any other bands except the one which is at the Fermi level, where superconductivity is formed, which is already an approximation, okay? And the idea is that since I'm driving the system with terahertz light, maybe I can forget what's going on to very far energy. And then we have to couple the electrons, the gauge field to the electrons, and this is where the electric field is entering, and then interaction between electrons will be relevant to describe superconductivity or eventually other kind of correlation. Now, what was just mentioned this morning in the talk by Ryo Shimano and Kota Katsumi is this idea that the microscopic coupling of gauge field to electrons has two possible combinations. There is a kind of diamagnetic term where if you want two photons excite directly one electronal pair, and then there are current-like correlation when essentially the photon is exciting electronal pairs, and this is weighted with the velocity, if you want, of the electrons. And these are called diamagnetic-like processes, and these are paramagnetic light. And the point is that we want to build up processes which are third order in incoming field, and the blue line will be the detected light. And so we have different combination. And the different combination also means that these are Kubo-like processes where there is only one frequency running in the loop, while here I have higher order correlations, okay? And from the point of view of the superconductor, when we enter in the superconducting state, this electronic excitation carry on the information of the gap opening, and so there will be a different response in the metallic and the superconducting state. What about collective modes? In the typical language of Feynman diagrams, the collective mode will be vertex correction in the amplitude or phase sector. If you want to think about this one, essentially we are creating particle Hall excitation, which can decay in a collective amplitude or phase excitation. They recombine, and then we detect the light. Or in the language we were using before for the phonon, if you want the effective Raman coupling of the Higgs or of the phase mode to light, is still mediated by electrons. And then we have to compute this susceptibility to know how much light can couple to collective electronic excitations. Okay, so far the focus has been mostly on third harmonic generation. We have seen several examples this morning of why this is important in superconductor. And then I will try just really to make a long story short. And the point is again, which model I take to compute my nonlinear response. And then if we start from a simple interacting model where only the pairing interaction is taken into account, it turns out that the only relevant process for nonlinear response are these diamagnetic-like processes where essentially what we are measuring is a kind of density-like correlation function. And in this approximation, essentially only the BCS response is important in the nonlinear for the third harmonic generation, just because the Higgs mode is essentially uncoupled to light. If you want to look in this picture, the Higgs mode is a neutral mode, it doesn't couple to charge, and then the coupling is essentially zero. So both the BCS and the Higgs mode give it the same structure in frequency, so THG will be an answer with the omega equal to delta. Omega is the frequency of the pump, but from the quantitative point of view, the contribution of the Higgs is very small. And this is a result that we can only get going to macroscopic model, not to effective description, like Gisborne-Landau model. And from the point of view of, for example, studying superconductor, in this limit, the response that we get from there is the same as spontaneous Raman in the effective mass approximation, which was somehow used for a very long period to study Raman, for example, in cuprates. Okay, so in a sense, THz spectroscopy is trivial. And then Raman spectroscopy will tell you, okay, why I should use a laser and spend millions to make a lab where I can do spontaneous Raman. Yes.
Yeah, I guess I'm looking to understand, like, is this response, what nonlinearity are you actually, is this the nonlinearity of band structure and the BCS Hamilton? It's like,
is the fact that you open the gap somehow makes the metal
curvature.
Yes, so you make possible to have.
So this must be really small and weak, and the BCS limit negligible somehow.
What do you mean?
In other words, if I take the BCS limit where the gap goes to zero, this whole thing just disappears.
What do you mean the BCS limit, the gap goes to zero?
I want to know, like, can I rescale the gap magnitude out of this?
Okay. Okay, yes, somehow this scale more than with the gap with the kind of interaction that you have, so the pairing interaction. So yes, so essentially this number is also expected to be quantitatively small. So I agree with you, yes.
A question and a half. Question, can you give me some intuitive way of thinking of the reason why in the clean limit, the Higgs doesn't really contribute very much, whereas the pair breaking? Because
the point is that you need to know which kind of correlation function your experiment is probing, okay? So nonlinearity is a generic statement. So what I'm saying that the nonlinearity comes from density-like correlation. And so you have a charge at the density fluctuation and the Higgs is neutral. So do not couple to each other. This is a very rough way to see this, okay? And then you have to go to some other, you have to look to some other way to couple the Higgs to light. Or if you want to say in another way, the light will excite Higgs fluctuation, but the contribution of Higgs fluctuation to the field, the nonlinear electric field that you detect is extremely small.
But there's something special to the clean limit with the quasi.
It's special to the clean limit. It's a and the reason why it's special, and then I'm going out to the disorder, is because somehow what happens is that these paramagnetic-like processes, also you would expect them to be relevant, but somehow there is a kind of very strange cancellation between positive and negative if your bands that opens in the superconductor exactly in the clean limit. As soon as you have a bit of impurities, you break, if you want, translational invariance, this current is more conserved and then you have a fine response. But so this is not different.
The half question now. But then because in the clean limit, linear spectroscopy doesn't show you the gap very clearly.
Yes.
Maybe that's good too.
Exactly.
Right.
It's the same. This is what I wanted to say.
Let's do third harmonic in all the clean limits.
Again, if you want, if you look at the linear spectroscopy, if the system is not disordered, you don't see any absorption.
Exactly.
Okay? Exactly for the same reason, because these absorption processes are mediated by the current, they go to zero. Okay. But then what happens here is that you find that when you put disorder, then you activated these processes, and there are two effects. One goes also with the question we had before. The nonlinear response becomes just quantitatively much larger. If you look at the scale here for the same, if you want a pairing interaction, here you have orders of magnitude larger THG response. And on top of that, you can also have that the Higgs mode becomes more coupled to light, and then it can even contribute more to the response and not to the BCS response. It happens the clean limit. But then everything becomes a matter of numbers, if you want. So the take-home message would be that if you just look at THG, which is an experiment done with a single pulse, okay, we know that in the dirty limit, like for NBN, Higgs will dominate, so what we are getting out of the system is a response of the Higgs. In the clean limit, which is probably the one relevant for most of the unconventional superconductor, the BCS response will dominate. But then you have to take a model to do a calculation to estimate how much one is big with respect to the other. And there is no way to distinguish them from the point of view of spectroscopic content, because the maximum response in both cases is obtained when the frequency of the pump matches the value of the gap. So can we do something better? And doing something better means to have a protocol which allow us to distinguish, if you want, two particle from one particle correlation function. And this can be done increasing the number of light paths that we use, because then we can really go to, if you want to look at the internal structure of this correlation function, then eventually distinguish between paramagnetic and diamagnetic process. So this is, if you want, an experimental way to try to check what is the important correlation in the system. And this was done actually by Peter and by Kota in the experiment that Kota discussed this morning. Let me just remind you what Kota already showed you. Essentially, you are in this nonlinear spectroscopy done with this 2D spectroscopy. You can completely remove, if you want, the linear contribution to the of the response. Then you can access the contribution of nonlinear processes to the third harmonic, which are this one. Okay. That is absent usually in the third harmonic in transmission. And then the experimental observation is that if you compute now the nonlinear contribution to the first harmonic, this one is temperature dependent, and you have the maximum response when the value of the narrow band pulse you're using matches the value of the gap, which is different from the resonance that you see in third harmonic, which is larger when twice the value of the pump matches twice the value of the gap. Okay, so this is an experimental observation, and then the consideration we can do about that is that, again, if you wanted to compute how the magnetic-like process or paramagnetic-like processes contribute to the first harmonic, we just discovered by using this argument that resonance occurs when the frequency flow in the line is equal to twice the gap, that there is no way to get enhancement in the first harmonic coming from the magnetic processes. Only this paramagnetic process can explain a resonance in the response when the frequency matches twice the values of the gap. And this is, again, a result which holds regardless the exact value that we get of these two contributions. So if you want, this experimental observation is a validation of the theoretical approach, regardless exact numbers we put there. So this experimental observation tells us that we are really measuring current correlation function, which are not seen in spontaneous Raman, and make the errors different from somehow spontaneous Raman. Then on top of that, we also found that there is an important, now it's stuck it. Okay, I have no way to go on. There is also a contribution to from the Higgs, which is becoming more important. And these are the results done with the numerical simulation with the attractive Hubbard model we disordered. And you see the dashed line, the BCS part, and the solid line, the BCS plus the Higgs. And the contribution of the Higgs here is really huge. And we have some idea why this happens, because somehow the topology, this diagram is different from the one that we get in third harmonic, but we still don't have a full, let's say, analytical theoretical understanding. What we also observed that the result is robust as a function of disorder. So going from the dirty limit to the clean limit, you see again the scale of the overall response changes, but still the Higgs is dominant for omega equal to delta, which means that we can say that third harmonic is a preferential tool to measure Higgs fluctuation in clean superconductors like Coop rates. Okay, so this was nice, but then the experiment that I show you so far was obtained with taking two pulses, but they overlap in time. So the time difference between them actually is 0. And then the question is that can we extract the same information that I discussed so far going to 2D? Because from this kind of 1D or tau equal to 0 experiment, we had to go in temperature to distinguish different contribution. But can we instead looking at the single 2D plot taken, for example, to the lowest temperature and exciting the system now with broadband data? And the answer is yes, because actually the general description I'm giving of the system of the problem is that the nonlinear current is a convolution of a nonlinear kernel, which is where excitation of the system and their coupling to light enter, and the shape of the pulse that I'm using. Can be broadband, can be narrowband, and can be filtered, for example, by linear response. So in principle, the scheme is general, and we can apply it to interpret this data. And how we take into account the presence of two pulses, I just make a replica of my total gauge field with the second pulse and the first pulse, which will center to a time t, which is negative, if you want, in the time delay. This goes in the Fourier transform, and then I can easily write down the nonlinear response as a function of the detection frequency and the time delay between A and B pulse in this way. And then you see, you can now play in very simple cases with this formula. You can, for example, distinguish between experiment done with the narrowband pulses or broadband pulses. And then if you have narrowband pulses, essentially what you get is that your A field has only one frequency. And then you usually have this 4 spot, and the only information you get about the kernel, so the response of the system, is eventually encoded in the relative intensity of the peaks. So you could, in principle, just looking at the intensity, tell if you have diamagnetic or paramagnetic processes, but this is, of course, rather difficult also from the experimental point of view. The two pulses are never exactly identical. So that would be very difficult to identify in this way. So if you want, in this limit, what predominates in this convolution is the structure of the pulse. But if you go in the opposite limit, where you have broadband pulse, let's say completely impulsive limit, these are constant, then you get the resonance of the kernel. And then you can even draw where the main features will be in the omega t versus omega tau plane, just looking at the possible combination of the 3 frequencies here in the kernel, matching the value of the resonance. And here you can have a horizontal, diagonal, and vertical, essentially, response. So in reality, the system has pulses which are never infinitely broad, and then you have a kernel with the resonance which are not infinitely sharp, and then you can just compare the narrowband experiment with the broadband, and you can just model what is the response of your kernel according, for example, to what the information we learned from the narrowband data. And then you can compare the calculation with the experiment, and then you just see that the main contribution to the 2D plot comes actually from paramagnetic response. So if you want, this is a way to extract directly the information, which are the most important correlation in the system, extracting, if you want, the information on the kernel from the 2D data. And we gain resolution because we have 2 pulses instead than 1. Okay, and so we can really say how the excitation is going on. Let me just mention that there is also an additional contribution here in the experiment that we model like incoherent response, which, if you want, is like a resonance in 0 frequency, something which is structureless. This is always there in the experiment. This is something which goes beyond any equilibrium calculation. So somehow you have to put by hand, but more intense your field, stronger will be this incoherent response. And this can eventually completely dominate the 2D plot when the field is very strong. And this has been seen actually in experiment by other groups. Okay, let me just make, do I still have a few minutes? I just want to make another example, which is, again, a completely different, if you want, problem, but still connected to superconductor, which is the physics of the Josephson plasmons. And Andrea told us something this morning. So in this case, usually we are used to think not in terms of microscopic model, but in terms of effective model. And the effective model is just a model for the phase degrees of freedom, So we imagine that we have a phase which is defined in each layer, and the current between these layers is just the Josephson current between neighboring layers. There is a single energy scale, which is, if you want, the stiffness in the out-of-plane direction, which also controls the out-of-plane plasma. Now, if you stay within this picture, and we ask what will be the response into this spectroscopy, you have to consider two effects. First of all, that the Josephson plasma has a contribution linear response, which essentially filters out the outside field, giving the main component inside the sample, which is the frequency of the plasma. And this is affecting that is there already in linear response. From the point of view of nonlinear response, the kernel, if you want to take into account the excitation of the system, in this case, a process where light can excite to plasma with opposite momenta. And here one has to put the wall dispersion of the plasma, the polarization of the light, and this can be done with care, and there is a very recent publication by our group where this is discussed. But let me go to the final result. Okay, so we have a filtering effect, if you want, of the linear response that tell us that the main component of the field inside the sample is the frequency of the plasma. And then we can have a contribution to plasma excitation, which again is largest when the frequency of the pump matches the frequency of the plasma. But for low temperature, this filtering effect is dominating. And this is what essentially can be used to reproduce the experiment. There is the issue of the homogeneity on the value of the omega C. This was beautiful demonstrated experimental in this recent work by Andrea. So somehow you can look at, you can just simulate in a almost analytical way what is the response of the system. These are the 4 spots here, which are located at the frequency of the plasma, just because if you want, the only frequency which goes inside the sample is the frequency of the plasma. And then the Josephson echo, which is the typical, the lowest spot here, gets strongly deformed by the presence of an homogeneity in the distribution of the plasma. And this is exactly the point that we started from this morning in the slide that also Peter showed. Also, the other peaks can be affected by homogeneity, but in a way which is probably less evident than the Josephson. I just want to make one last comment, because this will be probably discussed later on by Olivier. There is if you look at the shape of the peak, it's important to understand if you include in the Fourier transform also data for negative tau, because the shape, especially for this structure, changes considerably. This is something which is obvious to theorists. I don't know how much this is obvious in the way theorists talk to experimentalists, but this is just something that has to be taken into account if you really want to make a statement based on shapes of the peaks, okay, not on the position. Okay, so last comment, I tried to convince you at the beginning that we don't have to use effective model. We have to do macroscopically. But then I discussed the plasma within the context of Josephson model, which is a reasonable model for degrees of freedom. But even in this case, we know that macroscopic level, again, the gauge field couples to electron, then we should integrate out the electron and see how much the coupling of light to electrons mediate excitation of the plasma. Now, for low temperature, usually the XY model is a good way to describe phase degrees of freedom, at least in a qualitative way. But when we go to finite temperature, finite disorder, finite frequency, we know that the microscopic model will be anharmonic in the phase degrees of freedom, but the coupling that we get in the higher order terms doesn't have to be the same with what we have in the second order term. And this can be important in comparing the theoretical calculation with the experiment done, finite temperature, finite frequency, and finite disorder, okay? Okay, then, okay, which is also something relevant for the last experiment by Andrea that actually, unfortunately, Andrea didn't show this morning, so I cannot refer to that. So let me come to the conclusion. I try to just make an overview of why macroscopic approach is important, at least in cases where we don't have adiabatic decoupling between fermionic and bosonic degrees of freedom. And then all that I discussed today is based on a full frequency approach to this spectroscopy, which is very unusual because we are very often used to think about experiment or observation in time, but actually frequency is the Fourier transform of time, and the reason why we do calculation in frequency because it's much easier to include correlation in that language. But there is no reason why we don't have to describe to this spectroscopy taking the same approach, just going beyond the linear order and including all the macroscopic effect in the way that we know how to do. And with this, I close, and I thank you for your attention.
Okay, if I take the echo peak,
Okay.
So the 1 minus 1 peak,
Sorry, what were you talking
the
about?
echo peak,
The echo peak, okay.
1 minus 1. And I compare it to the 1-1 peak, which is the one where you see this effect of the two plasmas. Can you, so in your model, so does the echo peak also have the signature of the two plasmas?
Okay. In this case,
So
I don't have it here, but yes, I mean.
All right,
the
ones you're showing there on the right, is that the echo? Is that the 1-1 peak?
This
That's the
one is
1-1 peak, the one on the right.
This is the echo.
Okay.
Now, as I said, if for some reason, so either because you pump the system with the multi-cycle pulse, or you pump the system with some field which gets screened, if you want, inside the sample, you only have one frequency. The only way to distinguish the nature of the kernel is to look at the relative intensity of the peaks. Okay, so in this situation, for low temperature, where you have a strong filtering, there is really, I can show you the simulation done adding or not the two plasma, you will see no difference. Because what predominates in this kind of a single frequency experiment is just the structure of the frequency which is driven in the system. So if you want to, you can say, no, I don't want to shut down. Sorry. If you look at the same configuration for superconductor here, sorry, here you have 4 spots because you're driving the system with the multi-cycle pulse, so almost monochromatic in frequency. Now, do I get an information of what is the real mechanism giving rise to nonlinearity? Yes, you should look at the relative intensity between peaks, but this is something which is almost impossible to do it in experiments. Okay, what I'm saying is that in this monochromatic limit, it's very difficult to get information on what is the driving mechanism behind nonlinearity. You have to go to a situation like this one to make a distinction. So you have to go in a situation where what dominates this frequency convolution is the structure of the kernel, not the structure of the pump. So the bottom line is that for your data, especially in the low temperature regime, it's very hard to get any information about the two plasmon kernel just looking at this data. In addition to the fact that in your case, you cannot compare the intensity because data are acquired with different direction. I'm not sure I answered your question, maybe we can discuss it later.
Maybe you had, but if you had said it in Japanese, I would have understood this. I would have gotten the same amount of information. We got to talk about this later.
Okay.
Your questions? Yeah.
So your diagram of the magnetic coupling of the Higgs
yes.
Has been so far neglected, right?
It's been so far, sorry?
Neglected.
Ignored. So it's become
this one?
Yeah, that one.
This one is being ignored.
It's due to the lattice model.
No, it's not because of that. It's just because we were looking at the third harmonic generation so far. Now, these diagrams give a contribution to the third harmonic generation to a frequency which is much larger, omega equal to 2 delta, even there. But nobody was measuring third harmonic generation in that resonance condition. So we just, didn't look at frequency larger than the gap.
Yeah, but my question is that term is also finite even for the continuous model?
This one or the diamagnetic one?
On the right.
On the right?
Is the term?
Yes. So here the problem is not being continuum or being in the lattice. The problem is having or not a disorder.
But this means it's a Higgs couple. It's with one photon.
Yes. like what you have in optical conductivity.
Is it parity forbidden or it's allowed?
Not if you have disorder. So I can even say it in a different way. Even when you compute the optical conductivity absorption, you can in principle have a contribution of the Higgs to optical absorption if you drive, if the disorder is strong enough. Usually it's very small, but you could have some.
It's 1 photon.
1 photon.
Yeah.
So contribution of Higgs to absorption is 1 photon.
But Higgs doesn't have a type. It's,
No, it does not.
Still?
But if you want, there is disorder which is somehow saturating the momentum dependence that you have there. So if you think in terms of translational invariance, this is exactly 0. I completely agree with you. Exactly for what you have in mind. So it's like if you can think about disorder like giving a finite momentum to the, then this would be equivalent to what you measure when you do you drive finite current in the system.
Yeah, I just had a question about the diagrams. You had paramagnetic versus diamagnetic, but naively there's other diagrams too. I mean, you could imagine a kind of cubic vertex. You could imagine more diagrams than the ones you drew, right? You could imagine.
Yes, you can have combination of them. You can have combination diamagnetic and paramagnetic. You have all the
even a kind of cubic vertex where you have three lights that go to a single vertex.
Yes, so you have 2 coming in the same and then 1 coming here. So you mix the paramagnetic and diamagnetic.
No, I mean
Or
even
3 into 1.
Three on one. Yeah.
Okay, you can also have them. So actually, this is just sketchy for the talk. We computed all the possible diagrams, but these are the most relevant ones. Even here, I mean, you have another diagram. We have two lines, Higgs, and 2 lines there, and this is less relevant. We don't, as I said, I don't have still an analytical understanding why, but we are working with that. So to make a categorization, if you want, of which are the most important.
Other quick comments or questions? I think that really it's important, obviously, to figure out why this diagram is so sensitive, right? So it's
well, we are working on that. We're not lazy. I mean, we 2 months
Lara
ago.
and the other speakers for